Section 1 Introduction. In the past few years, we've seen a significant improvement in the quality of text-to-image generative models, thanks to advancements in diffusion-based techniques. These improvements are largely due to the availability of large open-source datasets for pre-training, better text encoders, improved methods for encoding latent images, and more efficient sampling algorithms. One promising alternative to diffusion models for generating images is the masked image modeling, MIM. MIM's ability to predict all tokens in parallel makes it particularly efficient for high-resolution data like images. Unlike diffusion models, which typically require 20 or more sampling steps during inference, MIM can generate images in as few as 10 steps. MIM's approach aligns closely with the well-studied field of language modeling, allowing it to benefit from the research community's findings in areas such as quantization schemes, token sampling methods, and token-based uncertainty estimation. MIM's default prediction objective is similar to in painting, and it has shown impressive performance in zero-shot in painting. Recent research in style transfer has also shown that MIM can effectively transfer the style of a single image, a feat that diffusion models have not yet achieved. However, despite these advantages, the adoption of MIM has been limited. The proposed architectures require significant computational resources, and previous models have not released their training code and modeling weights. We believe that an open-source, lightweight model will help the community to further develop MIM. In this work, we introduce aMUSEd, an efficient, open-source model based on MIM. aMUSEd uses a CLIP-L14 text encoder, SDXL-style microconditioning, and a UVIT backbone. The UVIT backbone eliminates the need for a super-resolution model, allowing us to train a single-stage model with a resolution of 512 by 512. The design is focused on reducing complexity and computational requirements to facilitate broader use and experimentation within the scientific community. We also demonstrate several advantages such as 4-bit and 8-bit quantization, zero-shot in painting, and single-image style transfer with style drop. We release all relevant model weights and source code. Token-based image generation has shown the effectiveness of VQ-GAN-generated image token embeddings for auto-regressive transformer-based image modeling. With large-scale text-to-image datasets, auto-regressive image generation can yield state-of-the-art results in image quality. However, auto-regressive image generation is computationally expensive. Generating a single image can require hundreds to thousands of token predictions. As images are not inherently sequential, MIM was proposed. MIM predicts all masked image tokens in parallel for a fixed number of inference steps. On each step, a predetermined percentage of the most confident predictions are fixed, and all other tokens are remasked. MIM's training objective mirrors BERT's training objective. However, MIM uses a varied masking ratio to support iterative sampling starting from only masked tokens. MUSE successfully applied MIM to large-scale text-to-image generation. MUSE uses a VQ-GAN with a fine-tuned decoder, a 3 billion parameter transformer, and a 1 billion parameter super-resolution transformer. MUSE is conditioned on text embeddings from the pre-trained T5XXL text encoder. To improve image quality when predicting 512 by 512 resolution images, MUSE uses a super-resolution model conditioned on predicted tokens from a 256 by 256 resolution model. Diffusion models are currently the prevailing modeling approach for text-to-image generation. They are trained to remove noise from a target image at incrementally decreasing levels of noise. Models are frequently trained on 1000 noise levels, but noise levels can be skipped or approximated without suffering a significant loss in image quality. Effective denoising strategies require as few as 20 steps to generate images with little to indistinguishable quality degradation compared to denoising at each trained noise level. However, 20 sampling steps is still prohibitively expensive for real-time image generation. Diffusion models can be further distilled to sample in as few as 1 to 4 sampling steps. This distillation can be repeated multiple times to produce a model that requires as few as 2 to 4 sampling steps. Consistency models can learn to directly predict the same fully denoised image from any intermediate noisy image on the ODE trajectory. These models were the first to successfully apply consistency distillation to large-scale text-to-image datasets, generating high-quality images in as few as 4 inference steps. Distilled diffusion models are faster than the current fastest MIM models. However, distilled diffusion models require a powerful teacher model. A teacher model requires additional training complexity, additional training memory, and limits the image quality of the distilled model. MUSE's training objective does not require a teacher model or approximate inference algorithm and is fundamentally designed to require fewer sampling steps. Section Summary. Diffusion-based text-to-image generative models have achieved impressive results thanks to large pre-training datasets, pre-trained text encoders, and improved sampling algorithms. However, the adoption of these models has been limited due to their computational requirements and lack of open-source code. In this work, we introduce aMUSEd, an efficient and open-source model based on MUSE, which demonstrates advantages such as quantization, zero-shot in painting, and single-image style transfer. We release all relevant model weights and source code to facilitate broader use and experimentation within the scientific community. Section 2.3 Interpretability of Text-to-Image Models. We're going to delve into the interpretability of text-to-image models, specifically autoregressive image modeling and MIM. These models provide explicit token probabilities, which are a good measure of prediction confidence. While we haven't fully explored the interpretability of these image models, we think it's a promising area for future research. We've trained a VQ-GAN model, which is a type of generative model. This particular model has 146 million parameters, doesn't use self-attention layers, and has a vocabulary size of 8,192. It also has a latent dimension of 64, which is a measure of the complexity of the model. This model reduces image resolutions by a factor of 16. For example, an image with a resolution of 256 by 256 or 512 by 512 would be reduced to 16 by 16 or 32 by 32 latent codes respectively. We trained this model for 2.5 million steps. We decided to condition our model on text embeddings from a smaller clip model, rather than the larger T5XXL model, to speed up inference. We experimented with two versions of the clip model and found that the original clip L14 produced better quality images. We used the standard cross-attention mechanism to inject the penultimate text encoder hidden states, and adaptive normalization layers to inject the final pooled text encoder hidden states. For the base model, we used a variant of the UVit, a transformer-inspired scalable U-net. This model can be effectively scaled by increasing the number of low-resolution blocks. We replaced convolution blocks with MLPs in the lowest resolution blocks. For our models with resolutions of 256 by 256 and 512 by 512, we didn't use any downsampling or upsampling in the convolutional residual blocks. The lower resolution UVit models receive an input vector sequence of 256 with a feature dimension of 1024. The model with a resolution of 256 by 256 has 603 million parameters, and the model with a resolution of 512 by 512 has 608 million parameters. The extra 5 million parameters in the 512 by 512 model are due to the additional down and upsampling layers. We used a cosine-based masking schedule, following the approach of MUSE and MaskGIT. After each step of predicted tokens, those with the most confident predictions are permanently unmasked. The proportion of tokens masked is calculated as the cosine of the ratio of the current step to the total number of sampling steps, multiplied by half of pi. We used 12 sampling steps in all of our evaluation experiments. We also micro-conditioned on the original image resolution, crop coordinates, and LAION aesthetic score. The micro-conditioning values are projected to sinusoidal embeddings and added as additional channels to the final pooled text encoder hidden states. For data preparation, we pre-trained on the LAION2B dataset, only using images with an aesthetic score above 4.5. We filtered out images with a watermark probability above 50% or NSFW probability above 45%. For pre-training, we kept the VQ-GAN and text encoder weights constant, and only trained the UVits of the respective models. The 256 by 256 resolution model was trained on two 8XA100 servers for 1 million steps, using a per GPU batch size of 128 for a total batch size of 2048. The 512 by 512 resolution model was initialized from step 84,000 of the 256 by 256 resolution model and continued to train for 554,000 steps on two 8XA100 servers. This model used a per GPU batch size of 64 for a total batch size of 1024. Finally, we sampled the percentage of masked latent tokens from a cosine masking schedule. We found that concave functions outperformed convex functions, possibly because they present more challenging masking ratios during training. Section Summary. The section discusses the interpretability of text-to-image models and the training details of the VQ-GAN and U-VIT models. It mentions the use of token probabilities for model interpretability and the potential for future research in this area. It also describes the architecture and training parameters of the VQ-GAN and U-VIT models, including the downsampling and upsampling techniques used for different image resolutions. Additionally, it discusses the masking schedule and micro-conditioning techniques employed during training, as well as the data preparation process. Finally, it mentions the use of cosine masking schedules and the sampling of masked latent tokens based on a uniform distribution. Section 4.2 Fine-tuning. In Section 4.2, we discuss the process of fine-tuning our models. We further refined our model with a resolution of 256 by 256 for 80,000 steps using the JourneyDB dataset. We also fine-tuned our 512 by 512 resolution model for 2,000 steps using the same dataset, along with synthetic images created by SDXL from Layan Coco Captions, Unsplash Lite, and LAION2B with an aesthetic score above 6. We noticed that the synthetic images created by SDXL from Layan Coco Captions significantly improve the alignment between text and image. We fine-tuned the 512 by 512 resolution model for fewer steps than the 256 by 256 model to prevent overfitting. To enhance the reconstruction of high-resolution images, we further fine-tuned the VQ-GAN decoder on a dataset of images with a resolution greater than 1024 by 1024. This fine-tuning was performed on two 8XA100 servers for 200,000 steps, using a per GPU batch size of 16, resulting in a total batch size of 256. In Section 5.1, we discuss the inference speed of our model, aMUSEd. It outperforms non-distilled diffusion models and is competitive with few-step distilled diffusion models. Compared to many popular diffusion models, aMUSEd scales well with batch size, making it suitable for text-to-image applications that require high throughput. For a batch size of 1, single-step distilled diffusion models like SD Turbo and SDXL Turbo perform better than both our 256 by 256 and 512 by 512 resolution models. However, as the batch size increases to 8, the generation time for SD Turbo and SDXL Turbo decreases significantly, while the inference time for our models decreases only slightly. Despite this, our models are significantly faster than non-distilled diffusion models and outperform the 4-step latent consistency model. In Section 5.2, we evaluate the quality of our models. We used zero-shot FID, clip, and inception score on the MSCOCO 2017 validation set with 2 samples per caption, totaling 10K samples. Our 512 by 512 resolution model has competitive clip scores, but both our 256 by 256 and 512 by 512 resolution models lag behind in FID and inception scores. Subjectively, both models perform well on low-detail images with few subjects, such as landscapes. They may also perform well on highly detailed images such as faces or those with many subjects, but this requires careful selection and prompting. In Section 5.3, we introduce style drop, an efficient fine-tuning method for learning a new style from a small number of images. Style drop has an optional first stage to generate additional training samples, which can be used to augment the training dataset. Our experiments show that style drop demonstrates effective single-example image style adoption on MUSE and aMUSEd. Other fine-tuning procedures, such as LoRa Dreambooth on Stable Diffusion and Dreambooth on Imagine, do not show the same degree of style adherence. In our experiments with aMUSEd, we achieved good results with fine-tuning on a single image and not generating any additional training samples. Style drop can fine-tune aMUSEd in as few as 1,500 to 2,000 training steps. Section Summary. The authors performed fine-tuning on their models at different resolutions and found that the synthetic images generated by SDXL from Layan Coco Captions improved text-image alignment. They also fine-tuned the VQ-GAN decoder on high-resolution images to enhance reconstruction. In terms of inference speed, aMUSEd models are faster than non-distilled diffusion models and competitive with few-step distilled diffusion models, especially when the batch size is increased. However, the aMUSEd models lag behind in FID and inception scores compared to other models, and they perform well for low-detail images but may require prompting and cherry-picking for highly detailed images. The authors also introduced style drop, an efficient fine-tuning method for learning a new style from a small number of images, which demonstrated strong style adherence on aMUSEd. Section 5.48-bit quantization. We've adopted a method known as 8-bit quantization, a technique borrowed from language modeling, to enhance our token-based modeling. This approach allows us to compress the model so that it fits into just 800 megabytes of video RAM, VRAM. This makes it possible to run the model on mobile devices and CPUs, which typically have less memory than dedicated GPUs. Our model, aMUSEd, can also perform tasks like altering images and filling in missing parts of an image, a process known as inpainting. These tasks are similar to the model's primary training objective, so we use the same decoding process. For image alteration, we mask a certain number of latent tokens, with more masked tokens resulting in greater changes to the original image. For inpainting, the mask we apply directly determines which tokens are initially hidden. We've also expanded aMUSEd's capabilities to include generating videos from scratch. We achieved this by modifying a method called text2video0, which works with Stable Diffusion's continuous latents. These latents are distorted by varying amounts to create the latents for subsequent frames, and then additional noise is added. To maintain consistency over time, we replace self-attention with cross-attention over the first frame during the standard denoising process. However, because aMUSEd works with quantized latents, we first need to dequantize the latents before they can be distorted, and then re-quantize them afterwards. Since the aMUSEd latent space is discrete, we completely remask the boundary of the image distortion, which results in consistent image backgrounds from frame to frame. We found that using cross-attention between frames reduced the quality of frames that were distorted too much from the initial frame, so we decided to perform the distortion later in the denoising process. In terms of ethics and safety, we've taken steps to ensure that our model is used responsibly. We've filtered out any images in the training data that have a watermark probability above 50% or a not safe for work, NSFW, probability above 45%. We've manually verified that both models do not accurately respond to NSFW prompts, leading us to conclude that our NSFW filtering helps prevent potential misuse of our model.